Hello? Hello? Hello. Can you hear me? Hello? There is no response. Hello? Well, if you guys can hear me, just let me know. Then I can start my talk. From my side, it seems like everything is working fine. Microphone and slides, everything is working fine. Can somebody respond me? If it is working fine, you can hear me? Hello? Hello? Hello? I just need to know if you guys can hear me. Then I can start. Still no response. I don't know if you can hear me. Can you guys hear me? Then I can start talking. Still no response. Oh, I don't know if you. Hi, Idris. How are you?
Hi, Shatan, how are you?
Good. Can you guys hear me in the conference? The audience can hear me?
I can hear you, but
Yeah, I can
the
hear
other
you
one,
too.
okay. Let me call the organizers. Okay. How are you?
Good. Can you guys hear?
Okay, let me call them. Okay.
Hmm?
Just a minute.
Yeah, I can hear.
Okay. I think someone is there and can hear us.
Dr. Biswas, we can hear you.
Okay, good.
Okay.
Thank you for
Start
confirming. Okay.
Start your talk.
Okay.
Okay, thank
So
you.
hi guys, myself Chandan Biswas. I'm from Center for Integrated Nanostructure Physics, Sangulgan University, South Korea. Sorry for this delay. I was here all the time waiting for you guys, but somehow this Zoom thing is very complicated, and that's why maybe you guys cannot able to connect me in the room. So anyway, so I think you guys had a good lunch. So hopefully I'll try to give a interesting and exciting talk. Otherwise, maybe you guys all be a sleepy cat or something. So let me try my best. So today my story will be on the exciton optoelectronics. We
Dr.
gonna
Biswas,
talk.
excuse me, you have time until 15 past 2.
15. Okay. So I will have 30 minutes, right?
No, less than 20 minutes. Because you started,
Okay.
we waited for you.
Okay, I will try my best to be more fast. Okay, fine. So we
Yes,
lost
please.
like
We will
20
wait
minutes.
otherwise. Yes, please.
Okay, fine. So I'll talk about the exciton optoelectronics, and this is very interesting nowadays because exciton has a very interesting properties, especially after the emergence of two-dimensional material. It become very interesting, and in future we may have very high efficient room temperature for superfluidity, or maybe people are working towards room temperature quantum computing using exciton nowadays. So maybe it is possible. At this moment, we don't know specifically. So anyway, let's start. So all this was possible because of many two-dimensional material now existed in our community. So we have all like a graphene, metallic graphene, semiconducting black phosphorus, insulating HBN, and semiconducting all two-dimensional material. And because of this existence, we are able to work on exciton nowadays. So basically, what is exciton? Let me clearly make you understand. So exciton is basically a electron hole pair. They bound together, like they have a very good love between them. They have a strong binding energy between them. So in 2D material, they bind very close to the atom, and they localize close to the atom, and the binding energy is very strong. In this case, you have like 1 eV, near about 1 eV. But in three-dimensional space, the exciton wave function is distributed throughout many atoms, but their binding energy become very less. In this case, like 10 milli-electron volt. But in two dimension, because their wave function is restricted in two-dimensional space, no z direction possible allowed here, only xy plane. So they can expand at the same time. They can have very high binding energy and also have large separation and longer lifetime. So basically, exciton is a bound electron hole pair. You can treat exciton as like a charged particle capable of diffusion, right? So this is like a very basic of exciton. Now, what we're gonna have with exciton. We have exciton, but in order to make futuristic devices and applications, we need this exciton to be stable at room temperature, right? Otherwise, if they simply die at room temperature, you cannot use it for further applications. So basically, you need exciton binding energy strength larger than the room temperature energy, which is like 25 millielectron volt. So traditionally in three-dimensional material, it was very difficult to have more than 25 millielectron volt because they have a high dielectric spinning. So the binding energy become very small, which is like 10 MeV or so. But in 2D material, the dielectric field lines are restricted in two-dimensional space. So the dielectric screening become very, very less. So when you have dielectric spinning very, very less, the effective dielectric constant also become less. And so in consequences, the exciton binding energy will be very, very high. So let me give you one example. So, for example, exciton binding energy in MOS2 is around 400 millielectron volt, WS2 around like 850 millielectron volt, which is far, far more than 25 millielectron volt. So that makes the exciton very stable with longer lifetime at room temperature, right? So now we can use this new particle for our futuristic device applications. So today's talk, I lost like 20 minutes or so, so I cannot go detail. Let me see how much I can cover. So I'll try to cover exciton properties in 2D, 3D interface and some application of that using graphene silicon Schottky solar cell. Okay. So first, if we talk about the exciton in 2D, 3D interface, there are many different type of exciton generate in this 2D, 3D interface. So basically, the 2D material is monolayer thick, so the whole material become two-dimensional interface, and it is highly, highly optically active. So, but when you excite light with this in this material, basically you generate many different type of exciton in the material. However, the binding energy distribution is not clear how in the real space how the binding energy distribute in the material. So this is like a an open question in the community, and this is a current challenge in the community. So we propose there is a way to do this by if we can measure the electrical band gap of the material by using scanning electron microscopy or STS in this case, and we measure the photoluminescence which is like optical band gap, and the difference between them would be your binding energy, and you can then map the whole sample, and you can see this color scale is basically your binding energy, and the whole sample you can see the binding energy how it distributes, right? So let me go fast, next slide, and go detail of this thing. So let's say you have 2D material now on the SiO2 interface, and you shine excite with light. So when you excite with light, many different type of excitons they generate in the material. Basically, you have electron hole pair, which is exciton. You can have charge state of the exciton as well. It's like electron hole electron or hole electron hole. That can be also generated in the material, depending on the laser excitation power. For example, um, when you excite the WS2 on SiO2 interface and you excite with very low power, you can get the PL signal. This is basically the exciton intensity you are giving, the number of exciton in the sample, right? So you can see the neutral state of exciton you can get in the sample, as well as a few charge state in the sample. However, when you excite with high power laser excitation, then you can see the neutral state become diminish and quench a lot and become very insignificant. In this case, the trion become very significantly dominant, and there's some new excitonic state they start emerging in the sample. Okay, so basically this data tell us that with the different excitation power, different type of exciton is emerging into the inside the sample. So if we try to plot the excitation power in the x-axis in this plot. So this is basically you are changing the excitation power, and here the exciton density. I mean, how many number of exciton, how many excitons are there in the sample. And this red line is basically telling you the neutral state of exciton. So with power increasing, the intensity, the number of neutral exciton is also increasing. And we see the charge trion here, charge exciton is a little less than neutral exciton, but after some threshold, the neutral exciton become diminished and become decreasing, and the charge exciton is dominates in this case, right? So this in this region you have a very high screening, carrier screening present in this case. That's why the charged exciton they can survive in this case, but the neutral exciton number of neutral exciton diminish. So we have a neutral to trion conversion having in this place. So in terms of energy, they become almost flat. I mean, not much change. However, for the charged exciton case, you can see their energy is slightly reduced at very high screening region. So this is normal phenomena that whenever you have a charged exciton in high electric field or high screening environment, you have the energy decays. So so far we got like exciton at low power, a neutral exciton dominates. You can see lots of neutral exciton, only one trion maybe. At intermediate power, you have a conversion from neutral to trion conversion happening, and at high power, you have lots of trion domination in this case. Okay. So if you see the whole flake and you can map actually which region having what kind of exciton. So this is the exfoliated sample, and we did the low power and high power mapping. And in both of the cases, you see in the middle of the sample, you have a strong defect induced trion signal compared to the edge of the flake. Flake edge dominates this neutral state of the exciton, but the mid flake domination of the trion is observed in this case. So this is very interesting, and we wanted to see more detail. So we did with different interface. So previously, this is the same data. This is previously we did with the SiO2 WS2 interface, and we compared it with another 2D interface. So this is like WS2 HBN. So this is 2D interface. This is 2D 3D interface. But interestingly, in this case, we don't see much peak shift compared to the 2D 3D interface, and that is there are some reason behind this. So the most important thing is this HBN is very good material and high electron mobility present in the WS2. So low carrier scattering happen in the HBN. So excitons are completely delocalized over all of the sample. And because of the delocalization, in order to induce this high carrier screening, you have to apply a lot of power. So how much power? That can be seen from this actually. So you see the same 2D 3D case. This conversion, neutral to trion conversion, maybe occurred at like around 20 microwatt excitation. But the same thing, in order to do in 2D interface for HBN, you have to go like 70 or 80 microwatt. So because of low carrier scattering in HBN, this interesting phenomena can be observed. So now further, the main point of this work is to have the distribution of the exciton binding energy. So basically, that can be done by the measuring the difference between the electrical band gap and optical band gap. So if this is the band gap of the material, this brown one can be measured by STS, like scanning electron spectroscopy, and this optical band gap can be measured by a PL, optical measurement, like photoluminescence. And the difference between them will give you this exciton binding energy. So when we measure this, basically we measure the electrical band gap, which is like 2.16 electron volt, and we measure the optical band gap of the material. So that gives us this exciton binding energy, but not only the one type of exciton. We can then analyze all different species, exciton species binding energy, like trion, defect induced trion, neutral, all these different binding energy we can analyze. So because of that, we are able to measure the binding energy with different excitation power. And very interestingly, you can see the neutral exciton is almost flat. Binding energy does not change much. But for the charged exciton case, the binding energy sharply increase. So this is basically you have a high binding energy from the defect induced ion, so which is they stay much with a much higher binding energy compared to neutral. So using this, we try to visually see how this binding energy formation is happening in the sample. So we can see the defect induced localization and binding energy is more higher in the mid flake, and in the outside basically you have all these neutral state are dominated. So this is very interesting. Now let me quickly go towards the application, my second topic, application of exciton. So basically in this case I um, choose graphene and silicon, a 2D 3D interface, because this Schottky solar cell is very easy to make and very interesting to see the charge dynamics in the material. So why Schottky solar cell is a simple device fabrication, comparably high solar cell efficiency compared to this polymer solar cell and other, and efficient carrier control can be done by doping. So, and then another question is why we are going to use this ideal diode solar cell, why this is important. So in normal solar cell, you have this typical nonlinear IV, which is not good for efficient charge separation. But if you have a like an ideal diode behavior, it is completely linear, so charge separation become very efficient, and that consequently improve the efficiency of the solar cell. So okay, now approach how we made this solar cell. This is very easy. You just make some electrode on top of silicon, and then you grow graphene and then transfer on top of that, and then you can apply your chemical doping on top and analyze the efficiency. So we simply did that. But one more important point, using graphene, the surface roughness become very smooth. So this is a typical topography of the real device. You can see the AFM morphology gives us the surface roughness become like 0.6 nanometer, which is like one atom roughness. So because of this very smooth surface, the charge scattering, I mean the recombination due to this rough surface is dominantly reduced, so solar cell efficiency get improved, right? So we use this phenomena to improve our device. And now we talk about the doping. We use the TFSA chemical doping, and we monitor the doping using a Raman spectroscopy. So you can see when we this is the compare, the pristine graphene, and when we try to dope with it, the G band and 2D band, the shift, red shift is there. I mean, the red shift occurs, and around like 30 millimole, you have a kind of saturation of the doping. So we found that 30 millimole is good enough doping for our case in that case. So if we measure the solar cell performance here, so pristine sample can see you can give like 2.8% efficiency, but when you have 1 millimole doping, it increased to like 5.8% efficiency, and 30 millimole gives you like 6.7% efficiency. So good, this is working. And then the question becomes why this is improving. And so we did some analysis, and then we found that the Schottky barrier height due to this doping is improved due to the the chemical doping. The Schottky barrier between graphene and silicon improved, and that makes it very efficient. So ideality factor also reduced very close to 1. So next, we try to observe is monolayer graphene is good enough, or we need more graphene layers, because monolayer graphene has lots of defect and the charge scattering is very high. But bilayer graphene case maybe improve the case, right? So monolayer graphene gives us efficiency like 2.8%, but if we use like bilayer graphene, efficiency little bit improved, not much, like 3%. But when you use this doping strategy on top, the efficiency goes to 9.5%. It's very huge, drastical improvement. And we see the ideality factor goes to like very, very close to 1.1. So device become very, very efficient. So same device, which was like 2.8% with doping, we can have like nearly 10%, which is very surprising and very, very good. But further, we improve it much further. We use some electrochemical doping as well. And using this electrochemical doping, we improve this device efficiency much higher than 9.5. So in this case, we use some EMI, TFSI liquid, ionic liquid, and we apply the bias. So this electrical biasing give the doping to the graphene as well, and that improved the ideality factor and consequent solar cell efficiency. So let's see how it works. So pristine graphene in this case gives you like 4% efficiency, and with 0.5 volt gate electrode, you can increase it like 4.3%, with 1 volt 8.6%, 1.5 volt 12%, and 2 volt it becomes like 13.6%, which is impressive, very good. So basically we try to see the ideality factor in this case become very, very close to 1. So it's become nearly like an ideal diode, and the conductance become completely linear, with this kink resistance become very low, like 42 ohm, which is very good. So these conclude as the electric chemical doping as well as electrochemical doping both are working fine, very good. What if we combine both of them? So we did that. We combined ionic gating as well as chemical gating, and then the shunt resistance become very, very high than the series resistance. Minded because this chemical doping reduced the series resistance a lot, and shunt resistance increased because of the barrier is getting better, right? So the efficiency in this case become 16%, and sorry, not 16, 13.6%, and it works like an ideal diode, which is without doping. This is at the low bias region it become ohmic, but at the high bias region it become space charge limited current. And minded the conductivity of graphene improved a lot because of the doping, so which you can see 180 nanosiemens, and without any doping it was like 130 nanosiemens, so which is very much improvement. So with that we improved solar cell efficiency, as well as we improved field factor, open circuit voltage, short circuit current, everything we improved by these two strategy. So if we compare this, if we benchmark this to other places with the reference, so this gives us very high efficiency, with very low ideality factor compared to the other work in the literature. So I think it is already maybe 20 minutes. I try to cover as much, but I would like to finish with the acknowledgement. This is I acknowledge our director of the center here, and these two works are done by these two Ria and Subhash. Without their tremendous effort, this was not possible. So thank you so much for your kind attention. If there is any question or if any time is remain, I can answer any question.
Okay. Thank you, Dr. Biswas. Is there any questions from the audience?
Yes, I have one for Shandan.
Yes,
Shandan, thank you very much for your excellent presentation. Did you try more than 2-layer, B-layer, 3-layer, or 4-layer?
Yes, we tried up to 4-layer, but if we use too many graphene, then their conductance does not change much.
Okay.
And mind it, if you use too many layering on the interface, then you will also losing the separation efficiency. Chart separation efficiencies will be reduced. So too much graphene is not good. And of course, if you use too many graphene, your incoming light transmittance will be reduced. So too much graphene is not good. We saw best result using bilayer graphene.
Okay, thank you.
Welcome.
okay. Thank you. Have a nice
Thank you.
day.
Thank
See
you.
you.
You guys enjoy. Yes. Thank you so much.
Okay, bye-bye.
Thank
Bye.
you, Shandan. See you soon.
See you. Yeah.
See you. Hüseyin. D var. Ha, D'yi dinleyebiliriz.
Saat uyuyor mu hocam? Saat uyuyorsa çünkü bazıları 5 dakika 10 dakikada olsa bağlanmıyorlar. Saatini bekliyorlar.
20 geçe bağlanması lazım. 25 geçiyoruz bak.
Aynen hocam. Soralım bir.
Bağlayabiliyorsa bağlasın bu şeyi.
Orada mı?
Görüneni. Ranjan değil. Hiç böyle durumlar yapar. Online çıktı. Bizde Malatya'da birkaç bir şey online bağlandı derken tam zamanında sunumun yaptığı konusunu aldı. Teşekkür ederim. Böyle
Alabiliriz hocam diyorlar. Eğer konuşmacı varsa.
tamam. Şeyi alsa şu en aşağıda bir kere.
Tamam.
Böyle de olanı alsa.
Hocam. Şey yapabilirsin. Ona bağlanabiliriz çünkü Ersin Hoca gelmediyse sohbette olan herhangi birine bağlanabiliriz.
Dr. Ranjan Dey, can you hear me?
Yes, I can hear you.
If you are ready, we can listen to your presentation. The previous presenter is not available at the moment.
Okay, fine. Okay, fine. I'll just share my screen with you.
Yes, please.
Is the screen visible to you all?
Yes, it's perfect.
Okay. Can you see my, just 1 minute. Just give me 1 minute. Okay. Can you see me now? Am I visible?
I cannot see you, but I can see your presentation.
Okay. I have put on my screen. I've put on my camera.
I can see now your picture as well.
Okay, fine. Yeah. Okay. So can we start?
Yes, it's yours.
Right.
Okay.
Right. Okay. Thank you. So I would like to start with a good afternoon from India. The time here is now 5 o'clock in the afternoon. And I am Ranjan Dey. And the topic of the talk today that I have is slightly different from the ones that I have been seeing. It is thermophysical properties of 2-pentanone and 2-heptanone plus some aromatic amine mixtures at 3 different temperatures.
Excuse me, Professor, can you presentation position?
Yes.
If you press F5,
I am already in the full screen mode, Professor. I can see
presentation.
Yes,
mode.
I'm in the presentation mode. I can see my screen in the full screen mode.
No, go to the full screen. Full screen.
Yeah, I've put it full screen.
Okay, then.
Is
Okay.
it not changing in your place?
Not yet.
Okay, I'll just escape this. Okay.
It is escaped. If you try again to full screen.
Okay, let me just try that.
Yes, that's correct.
Okay. So
Okay.
please let me know. Please interrupt if you see that the screen is not changing when I move to the other screen. So the topic of my talk is thermophysical properties of 2-pentanone and 2-heptanone, which we have tried to see how the interactions work with aromatic amine mixtures at 3 different temperatures. This work has been done by my scholar, Aditi Prabhune. She is a research scholar who is working under my supervision in the Department of Chemistry at BITS Pilani KK Birla Goa campus in India. Okay, as I can see that the slide is not changing when I'm changing the slide. So I'll just escape and maybe go back to the next slide. Okay, yes. So I would just like to brief all of you as to why we study thermophysical properties. And the simple reason for that is that they play a very, very important role in understanding the physical and the chemical aspects related to the solubility of liquids and liquid mixtures. And as a result of that, the properties that we determine are used in a lot of industries, especially those which are related to petroleum and pharmaceuticals. Now, the reason why we study this is because when we mix any two liquid mixtures, we find that the properties differ very, very significantly as when they were in the pure state. And so this study of liquid mixtures becomes very, very important when we are studying them in terms of ideal and their excess property behavior. Now comes, why do we study thermodynamic and transport properties? The reason for that is, of course, very standard. These properties like ultrasonic velocity, density, refractive index, viscosity, surface tension, and so many other properties which we normally study under the big heading of thermophysical properties give us a very, very good insight into the type of the intermolecular interactions which are taking place inside the liquid mixtures. Now, keeping that in mind, when we go to the background, then we find that these properties are actually somewhat different. When we say transport properties, then transport properties are different from equilibrium properties because they do not tell what is happening at equilibrium, but rather they tell that how quickly the equilibrium is attained. For example, if you look at viscosity, viscosity basically talks about the transport of the particular matter when it is going through a force. So it's a volumetric property, so as to say. The reason why these properties or their predictions have become very important in the past 1 or 2 years is, of course, due to the presence of COVID-19 pandemic, which all of us have been badly affected by. Especially India has been affected very badly, and labs all across the world were more or less in a shutdown mode, and almost no research activities were being carried out. So prediction of properties took a lot of center stage, and in the past few years, very good work and very good amount of investigation has been carried out in order to predict these kind of properties. So we also tried to do this kind of work, and that is more or less what the work is all about that I'm going to present just now. So the aim of the work was actually to take two alkanones. Those two alkanones are 2-pentanone and 2-heptanone, and then treat them with 3 amines, aniline, N-methylaniline, and pyridine, and then study it at 3 different temperatures. The reason why we undertook the study was because the alkanones that we have taken for the study are basically simple ketones, and they have a huge amount of applications. And the amines that we have chosen, again, the reason why for choosing the particular amines was because they are primary, secondary, and tertiary. And these amines are very, very frequently used, especially in the chemical, agro, and the pharmaceutical industries. So we wanted to see how these combinations actually give us what kind of properties and how the properties differ when we change from one alkanone to other. And of course, how we also see the interactions changing from one amine to the other at varying temperatures. That was the intent of the work that we wanted to carry out. So what we did is that we started firstly by finding out the isothermal compressibility. The isothermal compressibility, which is denoted by this beta T term. And this beta T term, of course, is found through the help of the adiabatic compressibility and the coefficient of thermal expansion. And having known this value, we were able to calculate the corresponding excess adiabatic isothermal compressibility. And when we plotted these curves, we found that all these values that we were getting, they were coming out to be negative. Negative excess values actually point towards strong interactions, but higher the negative value, the more is the amount of the interaction which is present in a particular system. Now, if we look at the values in the graphs, we see that this particular system, this which is blue in color, okay, I think the slide has not changed. Let me just escape and change the slide, right? So this last one, which is blue in color, is the one which actually is of 2-pentanone plus aniline. What it shows is that this system, which is the 2-pentanone plus aniline system, has the maximum interaction present, whereas the one which is of this orange color, which belongs to 2-heptanone plus pyridine, this has the lowest negative values of excess compressibility. And so it shows the minimum amount of interactions. So this was just one way to see that amongst all the systems that we have chosen, the 6 systems, that which one is the one which is having the highest interaction and which is the one which is having the lowest interaction. So this was one way to study how the interactions are actually varying by changing the components. After that, the next property that we studied was the coefficient of thermal expansion, what we call as alpha. And when we studied that alpha, we studied not only the alpha from the experimental values, but due to lack of experimental values at 2 temperatures, we also made use of an empirical relation. This empirical relation has been given in certain papers. It works quite well. So firstly, we tested the empirical relation. When we tested the empirical relation, we found that there was quite good agreement. Mind you, these values that we are seeing difference, they are all in the order of 10 power minus 3. So actually the difference is very, very small in terms of the numerical value. We also did the same thing for the isothermal compressibility, because again, data was not available at 293 and 303.15 Kelvin. So we use this expression again, which has temperature, density, and ultrasonic velocity of the liquid mixture. And here also we found that in all the 3 cases, the agreement was very good. And with these values, then we tried to find out more thermophysical parameters. Now, when we shifted to the other set of thermophysical parameters, so the first thing that we did is that we tried to find out the internal pressure. As we know that internal pressure is a very, very important characteristic property for liquids and liquid mixtures, because it gives us the idea of how much is the forces of cohesion and adhesion which are present in the liquid mixtures. So we found out what was the internal pressure. Now, internal pressure is fundamentally expressed by the change in the internal energy due to the change in the volume at isothermal conditions. And thermodynamically, if you want to find out, then the internal pressure is the product of the coefficient of thermal expansion times the temperature divided by the isothermal compressibility minus this pressure. Now, this pressure is the atmospheric pressure, and this is 1 numerically. I mean, standard we say 1 atmosphere, whereas this alpha T by beta T is in the order of almost thousands of atmospheres. So this equation actually reduces down simply to the internal pressure being equal to alpha T by beta T. And we have made use of this particular expression only in order to find out all these values that we have determined for the different alkanones under study that we have chosen. So what we find basically is that this internal pressure values are observed to be higher for the aniline systems. Whenever we have an aniline system, then the aniline system is always having a higher value of internal pressure as compared to the other counterparts. So that is one thing which actually it was, we were able to see that how the presence of the forces, adhesive forces, are affecting the variation in the internal pressure. After having done with the internal pressure, we thought, let us find out some more parameters, and we wanted to go ahead. And in doing so, what we did is that we naturally used the expression also to find it out at the other 2 temperatures. The other 2 temperatures, which were 293.15 Kelvin and 303.15 Kelvin. Since we had access to the data, the computational data of alpha and beta T, there also we found out the values, and we found that the values were all in a decreasing order. When I say decreasing order actually means that since the first component that we had chosen was the alkanone, so for alkanone, with the increasing value of X1, the internal pressure values were actually going down. So there was a decreasing trend which was being noticed, whichever was the alkanone under question, with the increase in the composition of that and a decrease in the composition of the corresponding amine. And so this was a trend which was being observed at 298 also. And we found that the similar kind of a trend was also being seen when we looked at the temperatures at 293.15 Kelvin and 303.15 Kelvin. After having done the internal pressure data, we moved on to other thermophysical properties, and we found out the energy of vaporization, the energy of vaporization is given by this expression, wherein we use the internal pressure data along with the molar volume, and also the enthalpy of vaporization, wherein we just add a term RT. It's a standard thermodynamic expression where the RT term gets added. And from there, we are able to get the enthalpy of vaporization. And there also, we found that this was a kind of a trend which we were actually getting, which was more or less in consonance with the properties of internal pressure, which we were noticing. So the trends are more or less in consonance with whatever was the properties or the values that we were getting earlier of the other thermophysical properties. We moved ahead and we wanted to find out some more particular characteristics. One of them, which happened to be the cohesive energy density, and the cohesive energy density actually depends upon the internal energy of vaporization, just the one that we had seen in the last slide, divided by the molar volume. And here we find that again, we were looking at a decreasing trend. Now, the reason why we study the cohesive energy density is because the cohesive energy density gives us actually an indication of the total intermolecular interaction energy, which contains both the specific and the non-specific interaction energies, which are present or which are prevalent within the liquid mixture. So as we know that cohesion is a resultant of intermolecular forces, especially the attractive forces involve hydrogen bonding dipole interactions. And this cohesion creates a large amount of pressure within the liquid. When we see there is a decreasing trend, then there is a decrease of cohesion, which is actually present within the liquid mixture. So that was the reason why we wanted to study how this variation is happening due to the variation of the alkanone. And we found that there was a decrease in the cohesion which was happening over the systems which were present at 298.15 Kelvin. After that, we thought of finding out the free volume because we had the available data with us. And the free volume actually gives us an indication of the amount of the space, the free space, which is existing between the molecules in the liquid. And as a result of that, we were able to see that the free volume and the cohesive energy density are basically move in opposite directions. And here also the results that we found, as you see, what we had seen in the earlier slide number 9, that there was a decreasing trend. So corresponding to that, when we look at the free volume, we find that the free volume is showing us an increasing trend. And what it actually showed again is the same thing that we had interpreted from the cohesive energy density, that an increase in the VF values actually goes on to tell that there is a lesser amount of cohesion which is present in the systems under investigations. So that was another thing which we actually were able to find out from these particular values. After that, we went ahead and we tried to find the most interesting parameter, which we call as the interaction parameter, because interaction parameter directly tells us a comparison of which particular system in question is having or is showing the maximum interaction which is present in a system. So the interaction parameter actually uses two components, or rather two parameters. One is the ultrasonic velocity U of the liquid mixture as compared to that of the ultrasonic velocity of the ideal mixture. And in order to find out the ultrasonic velocity of the ideal mixture, we use this fundamental equation, which is, as we know, the Lee-Urich equation. This is a very, very fundamental equation which is used in thermodynamics very, very frequently to calculate adiabatic compressibility, wherein adiabatic compressibility is equal to 1 upon U square rho. This was used in the reverse direction. And from this value of the ideal density and the ideal adiabatic compressibility, we reverse calculated the ideal ultrasonic velocity, and that is the value which was put in here for the calculation. Now, when we did that, what we found out was that these were the kind of the curves that we were getting. Now, normally what happens is that when we get interaction parameter curves, the higher is the value in the positive direction, the greater is supposed to be the interaction. That's how we understand it, and that is how it has been put in literature, in several literature. That is how the basically interpretation is done. If we look at this curve, then one thing becomes very obvious to us, that this curve, this is the black colored curve, which is belonging to 2-pentanone plus aniline, this has the maximum value. And so out of all these systems, 2-pentanone plus aniline, 2-pentanone plus N-methyl aniline, then 2-pentanone plus pyridine, and heptanone aniline, 2-heptanone NMA, and 2-heptanone pyridine, the maximum interaction is shown by 2-pentanone plus aniline, wherein if we look at the last one, which is this one, the blue colored one, then the lowest interaction is being shown by 2-heptanone plus pyridine. Now, this actually was the final, we can say the most conclusive parameter, which gave us a very, very strong justification as to how these particular systems are behaving with respect to one another, which has got the highest interaction and which has got, of course, the lowest interaction. So this was an important thing that we wanted to find out, because we had started by wanting to understand this thing actually. So let's now come to what we finally came to conclude from the thermophysical properties that we had ascertained. So what we found was that the internal pressure, of course, was decreasing with an increase in the temperature, and that showed that the strong adhesive forces were existing between the solvent and the solute molecules. The energy and the enthalpy of vaporizations were also showing trends which showed that the interactions decreased slowly with the respect to temperature. And the cohesive energy densities, of course, showed a decreasing trend, wherein the free volumes showed an increasing trend. And they both suggested that there is an increase in interactions as cohesion between the molecules decreases in the liquid mixture, something that we had already seen. The interaction parameter, of course, was very clear. It showed that 2-pentanone has the higher value than 2-heptanone. So this alkanone was showing larger interactions as compared to the corresponding 2-heptanone systems. Also, what we found was we wanted to segregate the systems in terms of the interactions. So we found that when the aromatic amine is a constant aromatic amine and we vary the alkanone, then the order is that 2-pentanone systems were showing higher variations as compared to 2-heptanone, wherein when we were keeping the alkanone constant and varying the aromatic amine, then in that case, the order was with aniline showing the highest interaction, followed by N-methylaniline, and then finally pyridine. So if we look now, if we just look at these two scenarios, I think we can very easily make out which is going to be the maximum interaction, 2-pentanone plus aniline. The one with the lowest interaction would definitely be 2-heptanone plus pyridine. And in between, we are going to have the other set of the corresponding systems, be 2-pentanone plus 2-methylaniline, then maybe 2-heptanone plus N-methylaniline, and then finally 2-heptanone plus pyridine, and then finally 2-heptanone plus pyridine. This possibly may be the kind of the order that we may possibly be looking at when we are going across the systems under consideration. Some more results that we were able to generate was that we found that the interactions, the reason why this kind of a trend was coming, why aniline systems were showing the maximum interactions, whereas pyridine was showing the minimum interaction, quite a few aspects were responsible for it. One of the factors which was responsible was, of course, the tendency of the hydrogen bonding capability of the molecules under question, which we were studying. So the H bonding capability actually decreases when we go from aniline to N-methylaniline, and is the lowest for pyridine. So because we are going from a primary amine to a tertiary amine. So at the end of the day, when we are looking at the amines, then the maximum interactions would always be shown by a system which is aniline as one component, and the minimum one would be shown by the one which has got a pyridine. The second, of course, aspect was that aniline had a very strong dipolar, you can say, unit as compared to pyridine. And so again, the H bonding was basically arising because of this strong dipolar unit which was there present in aniline. And also another interesting fact that both aniline and N-methylaniline are self-associated liquids by hydrogen bonding. But when this naturally will, of course, will give rise to a certain amount of interaction when it is reacting with a particular alkanone, which is not so much prevalent when you are looking at pyridine as one of the anilines, as the amines. Pyridine is actually highly self-associated, and the reason for that is that the nitrogen is present within the ring in pyridine, And as a result of that, pyridine is very stable. So that stability due to the hybrid resonance structure does not actually allow pyridine to interact so readily as it is in the case of your aniline and your N-methylanilene. So every system or any system which has got pyridine as one of the components would definitely show a lower amount of interaction as compared to the ones wherein you have got pyridine. Chain length was also playing a role, and we found that the chain length of the alkanone compounds were also affecting the molecular interactions, because once the chain length increases, then its ability to form the hydrogen bonding also basically decreases, and that was very much evident. Another interesting aspect that we found was that the polar nature of the oxygen atom in the carbonyl group, that was actually getting reduced because of the presence of a larger number of methyl groups. So as the methyl groups were increasing, this effect was actually going down. And of course, some basic fundamental factors always remained, like spatial accommodation, geometric fitting, and steric hindrance, which were of course responsible for these kind of gradations which were actually happening within the system. Now, we wanted to actually compare these findings with some of the findings which we had already published earlier. We have recently published our findings in Frontiers in Chemistry, Physical Chemistry, Chemical Physics in the year 2022 only. And this is a finding from there itself, where we had found out the beta T-excess values. And those beta T-excess values were for a lot more systems, not only these two, but there were actually 4 such systems. And out of those 4 such systems, we found that this was the kind of the effect which was coming. So 2-propanone plus aniline was showing, the maximum compressibility, whereas the 2-heptanone plus pyridine was showing the minimum. So here, of course, it was done much more extensively. Here in this work, we were not showing so much amount, but this has already been published. So I just wanted to go back and share that this is something which we have already validated. And as I said, higher the value of this isothermal compressibility, the larger or greater is the amount of the interaction which is present inside the system. So this is possibly because the molecules are able to fit better amongst themselves. There is lesser amount of space to move, and so that probably gives a larger negative value to the geometrical fitting which is present inside that particular system under consideration. This is some unpublished data I'm sharing with you. This is unpublished, means we have already communicated it. It's communicated data, but it's still not published. It's under review. So we have also done, we have found out the ultrasonic velocity. We have used different equations like Danuso, Vandy, Nomoto, Janji, collision factor theory. These are very standard equations which we normally use in order to find out ultrasonic velocity. We did a comparative value, and from that comparison, we found that the best approach amongst all these 5 is the one wherein we are using the Nomoto, this one, which is 0.69. This is the you can see this value that we are talking about, 0.69. This is actually the percentage absolute percent deviation. So it's the percentage average the percentage average percentage deviation, or as we might call it, is the absolute average percentage deviation. So AAPD, and from that absolute percentage deviation, we have been able to see that the minimum value is attributed to Nomoto, and the second one is second closest one is that which has been attributed to the collision factor theory. The highest values go to Danuso and Vandy because they look at ideal mixing, but since there's a lot of interactions happening within the systems, it is not ideal, and it is going away from ideality. Some more properties that we had found out was surface tension for all these systems under consideration. Surface tension values also showed a trend which was a decreasing trend, because that represents that is based on the ultrasonic velocity and the density. And so based on that, the Orbach equation was showing these kind of values which were there. And we found that these values were also in consideration with whatever values we have taken up till now. So all these values are actually communicated to a journal, and we hope that it will also get published very soon. We also did the interaction parameters for some more systems. These are all communicated systems. So these are all communicated properties that we have done. So I just want to share this with you. So the results, finally, the results that we got, and I'm concluding my work. So what we found that we had these, we had these 4: propanone, butanone, pentanone, heptanone in the overall study that we had chosen, out of which I took here only propanone and of course your pentanone and heptanone, but the actual study was for all 4, and these 3 amines which we had chosen for the study. So what we found out was that this was basically the variation when we saw that the amine was varied. So this was the order. So the maximum order was shown by propanone, and the minimum was shown by heptanone. So 2 propanone maximum interactions, followed by 2 butanone, then 2 pentanone, and least by 2 heptanone systems. Wherein when we came into the amines, then it was the maximum for aniline, followed by N-methylanisine, and for pyridine as the lowest. As we were saying, the nitrogen is right there in the ring, and so that presence in the ring actually makes it a bit problematic for it to resonance stabilization also helps, and so pyridine is a very, very stable molecule, and it normally doesn't really react very, very well. So I would just like to say that these are the scholars, these are the students. Aditi, she is the scholar who did majority of work on this. Another part of the work was done by Amrita, who just graduated. Just last month, she got her degree. She graduated. So I would now like to share some pictures of the place and my institute. So this is the original campus, the BITS Pilani campus, which is in the state of Rajasthan in India. This was opened up in the year 1963, and right now the government has conferred a very prestigious honor to the university in the form of Institute of Eminence. Only 5 such institutes were initially conferred with this award, and our institute is one of them. We have 4 campuses. So this is the mother campus, which is there at Pilani campus. Then we have another campus in India, which is the Hyderabad campus, which came up in the year 2008. We have a Dubai campus, which was opened in the year 2000, of course. And I, of course, work in the other campus, the campus which is, of course, in the beautiful state of Goa. It's a coastal, you can say, state. I had the opportunity of visiting Turkey in 2019 as a part of a keynote speaker in Thamam 2019. It was held in the beautiful, beautiful resort town of Çeşme at Izmir. I really wanted to come this year, but I had some pre-commitments. There were some courses, some classes, some more things I could not come. But I really, really wanted to come. And I hope that next time I'll certainly be able to come to the campus. So let me share some brief, pics of our campus just to tell you. So this is a beach, beautiful beach, Baina Beach, which is very close to our campus. This is an island, which we call as San Jacinto Island. And then, of course, we have the Majorda Beach, which is there. And of course, the BITS, which is at night. So we have some beautiful sceneries all around. And this is how the campus was looking up when it was lit up for the convocation last month. So this is basically the campus that we have. So I come to end of my presentation. I would like to extend my heartfelt thanks to the ICMATAC 2022 and the organizing committee, Professor Negdet Saglan, who was one of the persons who actually gave me the invite, to the director of our campus, BITS Pilani K. Birla Goa campus, India, my head of Department of Chemistry, and of course to my institute, BITS Pilani K. Birla Goa campus, India as a whole. Thank you. I would now be happy if there are any questions that you want to ask.
Thank you. Dr. Hey, for this nice pictures from your universe and for this nice physicochemical research, and you carried out the interactions between amines and ketone molecules. Is there any question from the audience? No? Okay, no more questions, Dr. Day. I'd like to thank you for your participation. Have a nice day.
Thank you.
Bye-bye.
Thank you.
Var mı hazırda kimse? Duyuyor musun?
O içerideki kumandalar. Soralım. Başka kim soralım?
Ya varsa sırada alt yakın varsa.
Sıradakini aslında bir saniye.
Next please yapalım.
Ben de yok. Online olarak kutulan da yok hocam. Şey de yok yani. Değil. Hocam yabancı katılımcılardan talep yok. Ama eğer şeyse Yasemin Öztekin çiftçi. O
Gelmiş
zaman
hocam.
bunu fiziksel olarak yapabilir.
Şey yapabiliriz. Tamam, ha burada.
Şu anda şeyde bekliyor. Yüz sunumunu istersek burada hazır bekliyor.
Tamam buyursun.
Ama-
Ama kahve arasından sonra önce yapalım.
Derseniz tamam derseniz bu alacağız.
Tamam.
Ama yani başka-
Sonra senin de
Gelen olursa artık söyleriz ama.
Uzat yapar mısın görüntüyü? Yine de.
Hocam anlatır istersen edeceğiz daha. Etmeden önce herkes anlatacağız. Şimdi işte
Ortası mesela.
Yani sevgi geliyor mu? Sevgi geliyor mu?
Hemen getiriyorsun.
Hadi arkadaşlar, gelin grup arkadaşlar. Gelin grup arkadaşlarımız da. Aşağıdaki zaman
Biliyorum.
29 arkadaşlarımız da geldi.
Geliyor öyle zaten.
Saygıdeğer başkanım. Ali Güvenlik Kal Bey'le
Yenisini istedi bulamadım. Eskisini konuşmayı. Ben şey yapmadan için çözdüm.
Şimdi kim de yeni istersen.
Harun burada mıymış? Daha burada var. Yok, yemeğe onu çağırsaydım madem.
Bana hiçbir şey çağırmadı. Sen uzaklaşma yakına gidin.
Yani Harun ne tutmuştu diye düşünüyorum.
Merhaba arkadaşlar. Şimdi Metalurji ve Malzeme Mühendisliği Öğrenci Topluluğu'na Organizasyon Komitesi Başkanı Sayın Profesör Doktor Hakan Ateş Bey'in bir plaket takdimi olacak. Buyurun Sayın Hüseyin Kalyon ve Sayın Organizatör Hakan Ateş Hocam.
Bir dakika hocam, arkadaşlar da geliyor. Hep beraber. Arkadaşlar iş olmayanlar mı?
Okay, we continue with our presentations. The next speaker is Yasemin Çiftçi. The stage is yours.
Hello, my name is Yasemin Çiftçi. I'm a lecturer in department. Today I'm going to talk about several electrical properties of advanced semiconductor rhodium tiny phosphate compound under pressure definition study. I would like to continue with outline. First, I will give basic information about motivation. Next, I will give some information theoretical background, and I will give the results, structural and electronic properties, transport properties, and finally, I will give the result and conclusion. Why thermoelectricity? Nowadays, there is some problem about energy. In this area of technology, energy is a key factor in the economy. In fact, our world run on energy. According to International Energy Agency, World Energy Outlook is 81% of total primary energy consumption is fossil fuel preserved in the form of coal, petroleum, and natural gas. So we need the energy. The reserved source of fossil fuel are limited, and we run out in the future. There is therefore an urgent need to use energy more efficiently and to find other sustainable forms of energy, such as solar, wind power, biofuel cell, etc. Among the ongoing direction, thermoelectric converter with high enough efficiency can serve well for both purposes. You can see here energy consumption rate increased with years. So we need to use energy efficiently. So what's the thermoelectricity? Thermoelectricity is a basic physical properties and is an excellent alternative for converting waste into electricity for efficient, environmental friendly, and maintenance-free cooling system and sound. Thermoelectricity consists of electrical current and voltages created through temperature difference within or between electrical conductors or semiconductors. Therefore, a thermoelectric material generates an electrical current. So in this graph, you can see here statistical results show that more than 60% of the energy is lost in daily. So thermoelectric material converts waste heat into electricity, and then we can use energy everywhere. What's the thermoelectric material? A material that can be used to convert thermal energy into electric energy or provides refrigeration directly from electric energy. You can see here some famous examples. These are chalconite and telluride, showing good performance thermoelectric. And Alpha alloys have recently shown great promise as thermoelectric materials. These materials are made of inexpensive, lightweight, and environmentally friendly elements. Many of these recent research efforts on these alloys have indeed focused on developing techniques to lower thermal conductivity while preserving the outstanding electronic properties. You can see in this graph alpha-style compounds showing smaller results of ZT parameters, indicating that performance of the thermoelectric materials. Performance of the thermoelectric material can be obtained by ZT parameter. In this formula, you can see here specific coefficient. Sigma is electrical conductivity, K is the thermal conductivity, and T is the temperature. Our goal is to increase ZT parameter. We need to increase ZT parameter, so we need to increase the Seebeck coefficient, electrical conductivity, while we need to decrease thermal conductivity. For this, only achieve it, doped semiconductor combining by electrical conductivity, combining by large carrier concentration and dose value and high mobility. To obtain our results, we used first principle studies based on density functional theory, and there is some approximation here for Ampere-Hayward approximation. And we solved in this study quantum evocation with non-interaction particles. And here we indeed of electron wave function, electron that we use on electron density. Our calculation involved three main steps. First one is optimization lattice parameters and internal structure. Second one, calculation of one structure using optimized structure. And the last one, solving Boltzmann transport equation for calculating different transport coefficient. First two steps can be obtained by WASP program. And here we choose pseudo-atomic calculation performance for, as you see here, and valence electron count is obtained at 18. Energy cutoff for pairing with this set is stated 700 eV. One-course key point used in the Brilliant zone, 14 times 14 times 14. And for the calculation transport coefficient, we need to use velocity, because the transport coefficient depends on the velocity of the electron. Velocity is obtained at one structure, so we need to use in great detail one structure. We increase the cup point mesh. Finally, I will give the results. First, I will mention about structure of this rhodium titanium phosphate. Rhodium titanium phosphate is a phase centrifugal structure, as you see here, and we have atomic position as you see here again. And we obtained optimized minimization and full relaxation, and that is equilibrium lattice constants, bulk modulus, ratio of theoretic bulk modulus, and band gap energy for this compound we tabulated here. As you see here on the table, our obtained lattice parameter is good equal with the other theoretical result. And as you see here, energy volume curve is radium for rhodium titanium phosphate. To see pressure effect on the transport properties, we applied on the lead cell pressure, and you can see here lattice parameter and volume, how it is affected from pressure. If we increase pressure, lattice parameter and volume, normalize lattice parameter and normalizes volume, it will with pressure. To calculate transport properties, we need to in great detail bond structure. In bond structure, you can see here there is an indirect band gap, and there is heavy and light hole, indicating that this compound can be used in thermoelectric application, because heavy and light hole, if there is a light bond in one structure, showing that large Seebeck coefficient and moderate electrical conductivity. And band gap changing with pressure, as you see in figure 4. How the elements affect the bond structure. We affected the bond structure. We calculated P-dose. You can see here near the Fermi level, rhodium D bonds is contributed muchly, and also strontium. Strontium D bond and rhodium D bonds causes this bond gap and affect the transport properties. If we increase pressure in this material, T-dose effective from pressure. You can see here if we increase pressure. After Fermi level, T-dose shifted higher energy region, but in under Fermi level, T-dose shifted lower energy region. Transport properties of this compound were calculated using vertical band structure and post-band transport theory. Rigid band and constant relaxation line approximation were also used here. And in this graph, you can see here for two different pressure Seebeck coefficient. Seebeck coefficient, maximum Seebeck coefficient is obtained at 600 Kelvin, and if we increase pressure, is obtained at 650 Kelvin. So we can say that temperature and pressure affect the transport properties and also improve this performance. In this graph, Seebeck coefficient and electrical conductivity depend on the chemical potential graphs. And for two different pressures, in this here, as you see here, Seebeck coefficient is obtained maximum value for 0.0 between 0.5. Between this region, this Seebeck coefficient is maximum and showing maximum performance of this compound. And you can see in this table, the maximum value of this Seebeck coefficient and electrical conductivity values. As you see here, P-type topping has maximum value than N-type topic. So we can conclude that this compound has good performance for Force factor is another important quantity indicating affecting performance of the thermoelectric material. Force factor can be obtained by this formula. So this region is P-type region, and this region is N-type region. According to this graph, force factor is also obtained P-type region and 600 Kelvin. And if we increase pressure, force factor increases with pressure, and also thermal conductivity. We need to decrease thermal conductivity because the thermal conductivity is below of the equation. So we need to log thermal conductivity. In this region, show the performance of this compound. And as you see here, also maximum value of thermoelectric factor for different pressure and temperature and pressure. And we have also obtained the temperature dependence of the transport coefficient. For this values, P-type topic and relaxation time, we obtained Seebeck coefficient and electrical conductivity versus temperature. And for the three different pressure, this was the Seebeck coefficient increase with temperature and also increase with pressure. And increase with temperature. Total thermal conductivity. We have obtained the total thermal conductivity also. And as you see here from this figure, that total thermal conductivity decreases with temperature. So temperature and the pressure affects high temperature affects the performance of the performance of the thermoelectric ZT value increase in temperature and pressure. Maximum ZT value was obtained. You can see here 0.62 at 950 Kelvin for 60 GPa. Our factor also increase with temperature and pressure. You can see here ZT formula here. And it is very important to calculate for thermoelectric properties ZT with temperature, because we can obtain this value experimentally. And as you see here, we obtained ZT value maximum 0.6, but it is not enough because we need to increase this value above the one value. We need to increase one value because showing good performance thermoelectric. And so maybe we can increase by docking or chain application. In summary, the electronic and thermoelectric properties of rhodium titanium phosphate were investigated under pressure by first principle calculation. The mixture of heavy and light bands needed the balanced band maximum lead to high thermoelectric power and reasonable conductivity. A theoretical analysis presented here predicts that rhodium titanium predicted rhodium titanium phosphate to be possible novel thermoelectric material, low value of lattice thermal conductivity. As a result, the temperature maximum ZT value was obtained when pressure increased and light high temperature. In addition, since the obtained value of ZT is not close one for this compound, so we need to improve with doping or strain application for it is used in thermoelectric application. Here are the references. Thank you for your attention.
Any question? Var mı kimse hazırda?
Var mı? Var mı? Sırada bekleyen var mı hocalarımızdan?
Var mı? Hiç kimse. Sözlü, online.
Bakalım hocam.
Online yok.
Hocam benim büyük çıktı. Ben anlamadım.
Tamam. Gel.
Onların sırasını almayayım.
Oğlanı anlatacağız abi. Tamam.
Var bir kişi.
Geriye.
Bir kişi var bir kişi. Bir kişi var hocamız burada. Tamam. Onu alacağız.
Nur hocam.
İknur Hoca. Hazır mı hocam? Hazırız hocam.
Hazır mıyız?
Evet.
Hocam açık şu anda mikrofon. Elimde de. Bir kere basıyorsunuz. İki kere basıyorsunuz.
Next speaker is İlknur Kars Durukan. Stage is yours.
Hello, my name is İlknur Karsturkan. I am working at Gazi University. I am working with Professor Dr. Yasemin Öztekin Çiftçi. This work is supported by BAP project. The title of my work is Thermodynamic Properties of Hall-Foister Semiconductor Titanium, Rhodium Titanium Antimony Compound. This is my outline. First, motivation, calculation methods, structural properties, thermodynamic properties, and then finally, conclusion. Motivation, thermodynamic properties are defined as characteristic features of a system capable of specifying the system state, suitable semiconductors to the fact that better available and tunable materials are interchangeable, provide a significant advantage to the technology and industry. Among various materials in use as semiconductor devices, the Hall-Foister alloys have provided to be promising contributions to the possibilities of turning the various properties to meet the desired demand. Hall-Foister alloys are ternary compounds and have cubic magnesium silver arsenide structure. These kinds of compounds have extraordinary electronic, elastic, optical, thermodynamic, and thermoelectric properties. The structural properties of various novel Hassler alloys are investigated for the precise understanding of the physics behind these alloys. Under the extreme conditions of temperature and pressures, the fundamental properties of the various properties of materials may change as compared to the ambient conditions. Therefore, the knowledge of thermodynamic properties under the variation of temperature and pressure acts as the extremely helpful tool of their technological applications in extreme conditions. The temperature and pressure dependent thermodynamic functions such as specific heat at constant volume, entropy, volume, thermal expansion coefficient, Debye temperature, granizen parameters have been investigated using quasi-harmonic Debye approximation. The thermodynamic parameters are determined in the pressure range from 0 to 20 gigapascal and temperature range from 0 to 100 Kelvin. This is my calculation method. The work is theoretical calculation. Density functional theory was used to apply to theoretical calculations by the Ab initio simulation package. The electron-ion interaction was considered in the form of the projector egg-mounted wave method with plane wave up to an energy of 7,000 eV. For the exchange and correlation terms in the electron-electron interaction, Purdue and Zanger type functional is used with the generalized gradient approximation. The key point meshes for Brillouin zone sampling is constructed using the more short PEG schema. At 16 cross 16 cross 16 more short and PEG, grid of key points have been used for integration in the irreducible Brillouin zone. Thus, this mesh ensures a convergence of total energy to less than 10⁻⁷ eV atoms. In this computational work to investigate the thermodynamic properties of rhodium, titanium, antimony, as a first step, a set of total energy calculation versus primitive cell volume was carried out in the static approximation. The results are then fitted with a numerical EOS in order to determine its structural parameters at pressure 0 and temperature 0, and to track the macroscopic properties as a function of pressure and temperatures from standard thermodynamic relations based on quasi-harmonic Debye model using Gibbs program. This work is figure 1, unit cell. Our compound is half-Hausdorff compound, and we can use atomic. We can use unit cell atomic coordinates. Rhodium. This rhodium is located 0.25, 0.25, 0.25. Titanium 0.5, 0.5, 0.5. Antimony 0, 0, 0. And space group F43M and space group No 216. And that's structural properties. Firstly, the equilibrium lattice parameter has been computed by minimizing the crystal total energy calculated for different volumes of lattice constants by means of Merlinger's equation of state, as in figure 2. We calculated structural parameters, lattice parameters, bulk module, and dry bulk module. We calculated lattice parameter 6.1 and theoretical value 6.14. This work is compatible with theory. The diagram that represents the normalized volume, unit cell, temperature at various pressure, and normalized volume pressure at different temperatures for rhodium, titanium, antimony compound being studied here are shown in figure 3. Note that for a given pressure, the volume is constant nearly with raising temperature. On the other hand, for a given temperature, the volume's unit cell decreases with increasing pressure. This result is apparently expected because commonly material expanded at higher temperature. Besides, the volume variation with temperature at lower pressures is stronger than a higher pressure. With pressure increases, the relative volume simply decreases for all different temperature series because material is compresses at higher pressure. In order to get an indication of the variation of hardness of the investigated rhodium, titanium, antimony, half-Foster compounds with temperature and pressure, the variation of bulk modulus with temperature A and B pressure of the compound are shown figure 4. It was observed that between 0 Kelvin and 100 Kelvin, there is a negligible dependence of the bulk models on temperature. However, above 100 Kelvin, there is a linear decrease for a bulk modulus with temperature. In addition, bulk modulus at room temperature attains values for 1014.69 gigapascal at zero pressure for rhodium, titanium, antimony compound. In figure 4, the relationship between bulk modulus and pressure increase linearly at various temperature. One can notice that the bulk modulus is an important parameter to define its resistance to volume change under compression. Granizing parameters is critical parameter and dimensionless quantity to describe the thermomechanical properties and anharmonic correlation in vibrating lattice. The variation of a gamma beta temperature at different sets the pressure in depicted in figure 5a. It is observed that gamma increases slowly with increase in temperature and different pressure values. However, the increase of pressure is more significant than that the temperature. The value of gamma of rhodium, titanium, antimony is in 1.726 at zero pressure and temperature, but its value is reduces to 1.427 at zero temperature and 20 gigapascal, resulting in decreasing anharmonicity in the lattice. A high value is gamma indicates high harmonicity in the compound, which results in poor lattice thermal conductivity. At room temperature, the value of gamma is 1.742 at zero pressure. And then Debye temperature thermodynamic parameter. Debye temperature is also one of the thermodynamic parameters that characterize the strength of the covalent bond and is related to electricity and heat capacity of the material. The evolution of Debye temperature as a function of temperature at different pressure and pressure at different temperature are figure 6. Debye temperature exhibits as negligible change in temperature domain 100 Kelvin and thereafter decreases with increasing temperature for at all of pressure. Clearly, Debye temperature decreases very slowly at higher pressure. the observed Dubai temperature exhibits a quasi-linear rising raise with pressure at a constant temperature. Furthermore, it is also clear that the effect of pressure and Dubai temperature is more important than the temperature. The computed value of Dubai temperature is found to be 331.34 Kelvin at 0 Kelvin and 0 gigapascal. And specific heat at constant value is another thermodynamic property related to the lattice vibration, internal energy path transition, and many other physical variables of the materials. The variation of the CV and a function of temperature at different pressure is displayed in figure 7. For a constant pressure, it is noticed that a 0 Kelvin and CV is 0, which means the absence of lattice vibration. Initially, CV increases linearly with the rise in temperature following Dubai T cube law. Therefore, reveals constant variation with temperature and covers to the long-fitted limits, which is behavior of all solid materials. At low pressure, the value is CV is larger than high pressure. At room temperature and 0 gigapascal, CV is obtained as 700 is 53 Joule cross mole Kelvin. And then our conclusion. Thermodynamic properties of rhodium titanium antimony half-Oyster compounds in the pressure range for 0 20 gigapascal and temperature of 0 1000 Kelvin were investigated with the Gibbs code. The bulk modulus at room temperature for the rhodium titanium antimony compound was determined to be 144.69 gigapascal at 0 pressure. The bulk modulus is important in determining the compressibility of the material, and anharmonic decreases with the increase in pressure. This indicates an increase in thermal conductivity. The Dubai temperature was found to be 331.34 Kelvin at 0 pressure and 0 temperature. And
Is there any question? Any question from our neighbors? No question. Yes, you have one.
You say that you chose Parvenz'in functional. What is the significance of this functional for your study? Why did you choose? Why not Parvenz'in, but Parvenz'in functional?
It is suitable for this structure, she says.
Right. What is the significance? Why it is suitable? Okay.
They have tried several models and then decided on this one.
Thank you.
After various trial and error, as I understood.
Thank you.
Okay. I have two questions. You said that you did some experiments at 0 Kelvin. 0 Kelvin. 0 Kelvin.
Yes.
Yes. How did you reach to 0 Kelvin? Yes. Yes. It's not experimental. Theoretical.
Yes, only.
Okay. And another one is, you said as the pressure goes down, CV increases. It was previous figuring here. At low pressure, the volume of CV is larger than high pressure. Why is this? Why? As the pressure decreases, CV is decreased, is it? Yani düşük basınçtaki CV yüksek basınçtaki CV'den daha düşüktür. Yani burada düşmeye belli olsun. Yani titreşim, örgü titreşimi değişiyor, internet enerji değişiyor, phase transition'i değişiyor. Evet. Tamam. Evet, evet zaten. Okay, thank you. Is there anyone ready to present? Yasemin, your group. All the afternoon session is your group. Is there anyone to present? Next one. Okay, go ahead. Downloading. Uploading. Okay.
Şey mi? Para veriyor muyuz? Sana para ver. Üniversite var. Var mı? Bir soralım bir. Devamı var mı? Hayır.
Next speaker is Gülçin Çorbacı. The stage is yours.
İleri.
Hello everyone, good afternoon. I am Gülsün Çorbacı and I am an undergraduate student in physics department at Gazi University. Our study name is Computational Study of Effects of Doping Nickel Palladium on Cobalt Aluminium for Hydrogen Storage Capacity, Elastic and Electronic Properties. Okay, you can see our outline here. Our contents, those are our main subjects. That we have first presentation and content demonstration. And then there's our study material. Which is okay. Here, there's models for getting the information. And carries. Solid state storage of hydrogen such as metal or complex cities is storing hydrogen with hygrometric and volumetric densities. In V2 intermediate flows, hydrogen generally shows a first methods can be practiced to study the hydrogen structure. Hydrogen stored in form of lithium and hydrogen it's more efficient than petroleum fuels. No, hydrogen is not non-toxic. Hydrogen is environmental friendly. Okay. So, hydrogen storage. Hydrogen is gas or suitable steel tank. Chips method stored underground in the big oil location. Store hydrogen in the key form So the cutoff energy of the plane wave is 700. The total energy is 5 flows over 10 minutes. 6 dB French atom. The increase is 0.02. So, about the threats. And the is 2.800. Position we have used logging using atom substitution as just talking to give you brand new. Modeling about aluminum alloy to prevent change in the structure. So much to aluminum. Compared to palladium atoms, small values, now structural properties. You can see the structure data of cobalt aluminum X, and X meaning nickel or palladium compounds under zero pressure within the metric capacity, information energy. You can see them to be reduced. It means that solution of interest the compounds are easily the greatest more components form. After doping the elements in cobalt aluminum, the formation the compounds lengthily formation of cobalt nickel aluminum and cobalt palladium aluminum offering between differentially takes cobalt atoms for the substation. Also, with hydrogen, after hydrogen, and after material reaction and indicate level of here we can see the formation energy is negative, and that for us the material is thermodynamic decision and experimental synthesis is possible. Also, we can see the material capacity, so we can say cobalt nickel aluminum hydrogen and more than the other materials. Okay. And here, calculate the elastic constants of another compounds. And you can see the criteria for structure and for tetragonal structure. Cobalt aluminum alloy in its element doping system have resistive structure and meet the bond stability criteria. After hydrogen doping, the crystal structures are tetragonal and provide criteria of elastic stability, but except cobalt aluminum palladium hydrogen. C1 values of all system except cobalt aluminum palladium hydrogen are large, indicating that the compound has strong line and compressive resistance in the x-axis. after hash doping hardness of cobalt aluminum alloy. So, so the elastic constancy for is important to us here because the elastic constancy for indicate to us the hardness of material. So we can say cobalt, nickel, aluminum, hydrogen is hardness than the other materials. So look at table 2. Okay. You can see in here that the calculated mechanical properties of cobalt aluminum alloy and its hydrogen under zero pressure in gigapascal, including bulk modules, shear modules, ratio of B/G, elastic modules, and Poisson's ratio. After hash doping increased, indicating that hydrogen increased the anti-fracture ability and ductility of cobalt aluminum alloy. After hydrogen absorption by cobalt aluminum alloy, the mass modules B/G ratio and Poisson's ratio increase, which indicates that hydrogen enhanced the ability of cobalt nickel aluminum hydrogen and cobalt aluminum hydrogen alloys to resist fracture and plastic deformation and improves the elasticity of the material. Hash doping has a significant effect on the mechanical properties of the cobalt aluminum compound. Here, the effects of nickel and palladium substitute additives on hydrogen storage and mechanical properties in an alloy were investigated, and their hydrides were investigated. Compared to the enthalpy of their formation, nickel or palladium atoms preferentially occupy the aluminum atom to form the cobalt aluminum nickel or cobalt aluminum palladium compounds. The B/G ratio and Poisson's ratio indicate that the addition of nickel or palladium can increase the ductility of the alloy, thereby improving the recycling performance of the alloy. Okay, now I would like to give electronic results for this compound in order to further analyze the effect of the doping atoms on the physical macroscopic mechanism of the cobalt aluminum alloy system. The total density of states, TDOS, and partial density of states, PDOS, are given in figure 2. So, according to electron bond structure graphs, cobalt aluminum and its hydrides exhibit metallic behavior. TDOS is an indicator of possible states of electrons in intervals between unit energy and number of quantum states. This is a key parameter for investigating the atomic bonding and material characteristics. The electron density at EF is non-zero, indicating metallic characteristics of the alloy before and after hash occupation. The dose in the low energy zone of cobalt aluminum, occupation of interstitials in cobalt aluminum crystals by hash atoms at EF is to reduce bonds high of total dose at EF. Enhance electron localization and covalent bonding energy and increase structure stability. So we can see from energy band gap graph that the materials is shown metallic properties because the transmission band and valence band coincide. And so we can see the hydrogen and aluminum bonds also in this graph. In this graph. Okay. After nickel doping, the effect of the cobalt nickel aluminum alloy in the low energy region is less, but the band with this alloy near the Fermi level expands. After hydrogen doping, the covalent binding effect increases and the compound becomes more stable. The intervening of the conduction and valence bands indicates that the material is metallic. This in turn can lead to the conclusion of a structure with a high conductivity. In cobalt nickel aluminum hydrogen is formed by hydrogen absorption by the cobalt nickel aluminum alloy. The S layer electrons of the aluminum atoms interact strongly with those of the hash atoms to form aluminum hash bonds. Okay. You can see the electronic properties in PD in here. As I said, like the other graphs. As you can see, the state of the elements in the graph, the cobalt aluminum compound shows semiconductor properties. Okay. The pseudo gap refers to the gap between the two doors, peaks near gap, and the pseudo gap energy directly reflects strengths of the covalent bonds. While pseudo gap energy bandwidth is to enhance covalent bond strength and compound stability. Figure 5 shows the pseudo gap energy of cobalt aluminum X, cobalt aluminum X hydrogen. Near AEF, it can be seen from figure 5 that pseudo gap energy of cobalt aluminum hydride is higher than that of cobalt aluminum, resulting in increased stability of hydrides. So finally, in summary, I would say that the result we have obtained. Here we have investigated the effects of nickel and palladium substitute depends on the hydrogen storage. And its mechanical properties in alloy and its hydrides are investigated. Compared with formation and copy of them, the nickel and palladium atoms preferentially occupy the cobalt atom to form cobalt aluminum nickel or palladium compounds. The B/G ratio and Poisson's ratio indicate that nickel and palladium doping could increase ductility of the alloy, thus improving the recycling performance of the alloy. As a result of the calculations, obtained results may provide an effective way and theoretical evidence for the better design and optimization of hydrogen storage materials. You can see our reference in here, and thank you for your attention. Do you have any questions? I'm ready for reply.
Any questions? Our young scientist,
Thank you.
how did you graduate?
Yes. No.
Okay, thank you. Yes, everyone. Next speaker. İlk durumunda değil mi? İlk durumunda.
Evet.
30 derece atmaz. İsteyinlerce bekledim. Good. Next speaker is Can Akkuş. İleri. Geri. Şurada koyarız. Lazer. Tamam. Geri. Kameraya doğru. Orada çok. Sensör oldu.
Dear ladies and gentlemen, welcome to my presentation. My name is Can. First of all, I would like to introduce myself. My name is Can Akkuş. I am an undergraduate student at Gazi University in physics department. So today I would like to going to talk about pressure effect on the structural, mechanic, electronic, and vibrational properties of platinum zirconium tin compound, AB initial study. I would like to continue with the outline. The outline of my presentation. First, motivation, calculation method, structural properties, electronic, elastic, and the vibrational properties, then result. The aim of our study was the PT-based Hausler alloys received much attention as promising semiconductors for high-efficiency power electronic devices due to its numerous optical behaviors, including its high absorption coefficient and to enable band gap energies, as well as its long-term stability. The main class of Hall-Heisler alloys is semiconducting materials, which can provide completely optical response. Here you can see the devices where Hall-Heisler materials are commonly used. The Hall-Heisler thermoelectric materials have been attracting the extensive research interest over the last 2 decades, owing to their thermal stability, mechanical strength, and the moderate ZT. These material systems are potential candidates for medium to high temperature application, which is the close to the temperature range of most industrial waste heat sources. In principle, the Hall-Heisler compounds form a terminus of variant of classical electron plus shell semiconductors, which crystallize in the zinc plate lattice, such as a galvanium arsenide. The 8 valence electrons are distributed among 3 atoms in of the 2. The third atom occupies the octahedral vacanions in the ZnC type lattice. This fact automatically leads to the formation of the rock salt-like substance characterized by ionic bonding interaction. The relationship between these differential crystal lattice is displayed in figure. Okay, this is the calculation method we use for this study, and our calculation methods are purely theoretical calculation. Firstly, density functional theory was used to apply all theoretical calculation by Vienna AB initial study simulation package. The electron-ion interaction was considered in the form of the projector augment wave method with the plane wave up to an energy of 700 electron volts. For the exchange and declaration terms in the electron-electron interaction, further van Zanger type function is used with the generalized in approximation. The K-point meshes for Brilliant zone sampling is constructed using the Moncross-Pack scheme. The 16 by 16 by 16 Moncross and the pack grid of K-points have been used for integration in the irreducible Brilliant zone. Thus, this may ensure a coherence of the total energy less than 10 to the minus 8 electron volt per atom. The pseudo-atomic calculation performed for PTZRCN, and you can see here on the screen, there is a value. The first of our calculation result is structure properties. You can see here the primitive unit cell and the compound unit cell of PTZRCN compound, and the atomic coordinates and structural parameter for PTZN compound you can see in the table 1. We can see in the table 1. Table 1 is the lattice constant of the compound, is with theoretical studies in the literature. The diagram of the total energy changes versus the volume changes of the unit cell gives the information about the structural stability. And here the pressure dependent of the normalized lattice constant and the normalized cell volume of PTZRCN illustrated in figure 2. Where the normalized lattice constant and normalized cell volume are the zero pressure equilibrium structure parameters. It shows that the applied pressure increased from 0 to 15 gigapascal. The ratio of the normalized lattice constant increases quickly. The second of our calculation result is elastic properties. The response of the solid under external forces is determined by the elastic constant. To obtain the second order elastic constants, the strain method is used to examine the pressure effect on the elastic behavior of PT0CM compound up to 50 gigapascal. The calculated second order elastic constant and the bulk modulus under pressure are listed in table 2. Obtained elastic constant provides the Born stability conditions indicating its stability mechanically. Elastic constant and bulk modulus increase with the pressure. The Poisson ratio is very important property for industrial application. For ionic crystals, and the lower and upper limits of the Poisson ratio are 0.25 and 0.5 respectively. And 0 gigapascal for PT0CM, it shows that the interatomic forces in the PT0CM are central forces and have ionic bonding properties. It shows that the interatomic forces, the PT0CM, are central, 0.3022 at the 0 gigapascal. As suggested by PAC, B/G ratio can discussing whether polycrystalline material exhibits brittle or ductile. As suggested by PAC, B/G ratio can discussing whether polycrystalline material exhibits brittle or ductile characteristic with a critical value of 1.75. It has been predicted that the PT0CM plays a ductile manner since the B/G is calculated to be higher, 1.75. And we can see here the elastic properties such as the Zener entropy factor, Poisson ratio, Young modulus are often measured for polycrystalline material, which are the most interesting elastic properties for application, were also calculated in turn to computed using the following relation. And we have the result obtained by using elastic constants. According to Born stability criteria, PT0CM compound of magnesium silver arsenide structure are mechanically stable up to 15 gigapascal and predict that there is not a transition phase when the pressure is under the 50 gigapascal. It can be seen in figure from 3. That C11 and the C12 varies substantially under the pressure when they compare the variation in C44. The calculation bulk modulus increases gradually as pressure increases, indicating that it becomes more and more difficult compass as the pressure increases. In this table, the Zener entropy factor is a measure of the degree of the elastic entropy in solids. The Zener entropy takes the value of 1 for a completely isoteric material. If the value of the Zener entropy is smaller or greater than unity, it shows the degree of the elastic entropy. This calculated Zener entropy factor for PT0CM is equal to 1.231 at 0 gigapascal, which indicates that this compound is anisotropy material. Obviously, the value of Zener anisotropy decreases with the increasing of pressure up to 50 gigapascal, which reveals that the degree of elastic anisotropy is getting smaller. Sound velocity also increases with the pressure. And for the third of our calculation results, the electronic properties, the band structure diagram for PT0CM along the high symmetry lines in the first Brilliant zone is shown in figure 4. This Fermi level is set to 0 electron volt and coincides with the top of the valence band at the gamma points, while the minimum of the conductive band at the X points, indicating that this compound is in red band semiconductors. We can also see here the energy band values at 0 gigapascal are very similar to the theoretical calculated value. And we also see that the band gap increases at the pressure value is increased. The partial loss of the PT0CM Hall-Poisler compounds are also shown in figure 6. We can analyze the graph given 6 in 3 parts: our valence band, Fermi level, and the conductivity band. The band gap near the Fermi level is due to the band D of PT and Cr atoms mainly, indicating that these states of PT and Cr play important role in physical properties of PT0CM compound. In valence region, the near of the -8 electron volt contribution of the S state for Cn is higher than Pt and Cn. The values of TDOS at Fermi level become smaller and the energy region near the Fermi level become wider with the increasing pressure. In addition, we also can note that the peaks of the TDOS being move to the low energy region. This may be due to the smaller of distance of the atom under compression, which leads to the change interaction potential. And our final calculation result is vibrational properties. As this compound has 3 atoms in the primitive cell in the phonon spectra of 9 phonon branches, including 3 acoustic branches and the 6 optical branches. One of the remarkable observation is that none of the branch involves a soft mode in the whole beryllium zone up to 15 gigapascal, indicating that this compound is stable dynamically. We have noticed that all acoustic and optic branches increase with the increased pressure. And finally, as for our constellation, ground state properties, PTZR-CN exhibits the semiconductor's behavior with a 0.97 electron volt band gap. The equilibrium thermal energy level is located closely to the valence band and the PTZR-CN suitable for the Fermi electronic application with a narrow band gap in the range of 0 to 1.3 electron volt. PTZR-CN is mechanically stable under the pressure up to 15 gigapascal, and PTZR-CN is soft material nearly, but besides it has comparatively high strength due to the large bulk modulus of 137.5 gigapascal. Applying pressure, this material can be hard. The ionic state in bonding is dominant for the compound. Its ductile character increasing along with the increasement of the pressure up to 50 gigapascal. PTZR-CN is stable dynamically up to 50 gigapascal. To the best of our knowledge, most of the studied properties are such as the elastic, the pressure effect on them are reported for the first time. And this is our reference. And thank you for your attention.
Question, John, for this nice presentation. So we know. Next, please. Keep going. This is the last one, isn't it? Is Selin Özden here? Selin Özden? Okay. So after this presentation, we are free. Not it. Ahmet Yönetken. No. Here's your presentation. Yes, ex-speakers Furkan Yönetken. Furkan Cil. Yes.
Hello everyone, my name is Furkan Cil. I am undergraduate student in physics department at Gazi University. Today I am going to talk about first principle study of effect on mechanical and electronic properties for CFPD compounds. I would like to start with outline. At first, we will start with motivation, then we will show you calculation method, and then we will show you some physical investigation of our studies materials, such as structure, electronic, and mechanical properties. As a motivation, rare earth intermetallic compounds have low specific gravity, resistance to corrosion, and structure and temperature behavior make them superior to ordinary metals. Scandium is the first transition metal elements and a member of the rare elements family, but does not have the unpaired 4f electrons. It has high melting temperature, close to iron, and small density, comparable with the density of aluminium. Scandium forms a series of ordered intermetallic compounds with the transition elements such as cobalt, radium, nickel, etc., and they exist in the cubic CSCl structure. CSTM compounds are of interest for application in the production of materials for spacecraft and electronic because of their structural and physical properties.
Can you chloride?
Yes.
It's not the air. Not the air.
Hocam skandium var.
Scandium. Such alloys are in the B2 structure and the PM3M space group. Scandium is a rare earth element with only one electron in the d orbital, and its compounds are considered candidate materials for spintronics. In our work, we have theoretically investigated the effect of single defect created by the replacement of vacancy or C, B, and atoms and this structure. Electronic and mechanical properties of the B2 structure CSPT compound. To obtain our result, we have used theoretical method. All theoretically calculated data in this study were made using the BUS program. They are based on density function theory using the projector amplified wave method. First, total energy calculations were carried out for the B2 CSPT compound without defect. Then the supercell was created. The supercell structure used in the calculations are made of 16 atoms of the B2 CSPT structure. The central position in the superstructure is occupied by a defect. The effect of single defect created by vacancy of replacement of C, B, and atoms on the structure. Electronic and mechanical properties of the B2 structure CSPT compound was theoretically investigated. I would like to continue result. First, I would like to give structural properties. In figure 1, the supercell form CSPT compound in B2 structure and representation of the structure formed by the addition of C, B, and vacancy are given. It can be seen from table 1 that we have obtained negative formation energy, indicating that this compound is stable dynamically and can be synthesized experimentally. The most biggest formation energy is obtained for defect of vacancy. The formation energy of the structures formed by the addition of additive atoms are given in table 1. The formation energy is obtained by the following equation. What is constant bulk modulus, volume, and total energy of supercell of CSPT and NIF structures formed by additive atoms are given in table 2. The lattice constant and bulk models of the CSPT compound were compared with the experimental and theoretical results, and results which are presented in the table 2 were found to be in agreement. Şu an geçti hocam.
That's okay.
Cn are very small elements in atomic diameter and mass. As can be seen in the table, the variation in the lattice constant and volumes is quite small. Bulk models is an important parameter to evaluate the stiffness of the structure. If we evaluate the effect of Bn and C atoms on hardness according to the substation of Cs and Pt, when the state is examined, we create hardness. The second result, mechanical properties. Young's methods can be explained as the ratio in tensile stress to tensile strain. The shear modulus is the magnitude of the resistance to plastic deformation that occurs when the material is stressed. G/B ratio is the ratio of shear modulus to bulk modulus and determines ductility or brittleness. If this value is less than or greater than 0.6, it is ductile or brittle. Poisson rate ratio is another parameter that determines the ductility or brittleness of the materials. The critical value for this is 0.26 if it is greater than or equal to this value, it is ductile. HV value indicates hardness. When this value is 10, the compound is hard, and when it is 40, it is super hard. Mechanical parameters are given in table 3. CSPT compound has a stable, ductile, and soft structure according to its mechanical properties. With the addition of additional atoms, the compound has preserved best properties. However, with the addition of vacancy or B, C, and N, the less change was observed with the addition of C atoms instead of PT, and the greatest change was observed with the addition of vacancy. The third last result, electronic properties. Evaluation of conductivity, state, chemical bond, structure, partial density of state. Band structure can only be realized by knowing the electronic properties. The energy band structure is presented in figure 2a with the total electronic state density along the height symmetry direction. In the graph with the Fermi level set to 0 electron volt, the overlap of the valence band with the conduction band at the Fermi level is proof that the compound has a metallic nature. You can see figure 3, electronic band structure obtained by the addition of C, B, and N defect on the CSPT spectrum. The partial dose of CSPT compound is also given in figure 4. The largest contribution to the valence band comes from the CSD orbital, while the contribution in the conduction band comes from the PTD orbital. You can see effect of defect atoms, partial density of state in figure 5. There is small contribution p orbitals of X atoms is conductive region. The effect on the electron properties by this displacement of the vacancy B, C, and N atoms instead of the CS or PT atom was investigated. The number of electrons in the Fermi level gives information about the conductivity. Electron numbers in Fermi level are presented in table 4. it was determined that the contribution of B to the conductivity was higher than that of C, N, and vacancy. Finally, would you like to sum up the result? In the CSPT intermetallic compound, a defect was formed in the compound by the replacement of the vacant B and C atoms with the basic atoms. Structural, mechanical, and electronic properties of that defective structure were determined. It was determined that the Bohr atom more affected the hardness parameter, and the Bohr atom increased the conductivity in the same way. You can see references here. Thank you for listening. If you have any question?
You have any questions? No question? Okay, thank you for your presentation. Don't think they're gonna want to. Does anyone else? Speaker? Ahmet Gönel'den İlhan Özkan birisi o Ayhan Erol here. No one here. I think so. See you tomorrow then. Ya. Ya. Şurada bir çeker. Bölüme vereceğim şu kalite konusuna. Ha bak ben ne kadar çok çalıştım. Ben de yazdım. Ben pazartesinden gelirken kalite başlayayım. Kalite konusuna vereceğim. Geleceğiz ben de kadar. Thank you.